EN. Membership in EN meant that somewhere we had that inequality satisfied. F of x plus h minus f of x over h in absolute value should be less than or equal to n for some x in the interval 1 to 1 minus 1 over n, and h in the interval 0 to 1 over n. So this was the defining property of being in n. And we also noted that any function that has a right-hand derivative anywhere at some point will be in one of the ENs. So the fourth step is to show that each EN complement is dense in the continuous functions 1, 0, 1. We already proved in part 3 that the ENs were closed. So this is an open set, and we want it to be dense. Now, to help us do this, we want some particular functions. So for each k, we define a so-called sawtooth function S sub k by the following. So I'm not going to write it down analytically, but I'm going to draw a picture of it. 0 to 1. And it's going to go up and down like that. So it's piecewise linear and continuous. And if you count the number of nodes here where the direction changes, you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Anyway, it's always going to be odd. So we take 2k plus 1 equally spaced nodes. And then to make sure that this, I want the function to be simultaneously small and with very large slopes. And I can do that. Take the height as 1 over the square root of 2k plus 1. Now all the slopes are the same, so we only have to compute the first one. So this says that the infinity norm of sk is 1 over the square root of 2k plus 1, which goes to 0 as k goes to infinity. And at the same time, the slopes, depending on where you are, they are plus or minus, or just compute the first one, the height over the distance so it's 1 over the square root divided by 1 over 2k plus 1, and that is the square root of 2k plus 1, and that goes to infinity as k goes to infinity. So in absolute value, these are very steep slopes. But at the same time, the infinity norm of the function is going to 0. So we'll need these functions in a moment. So we want to show that each En complement is dense. So let's fix N. And take a continuous function f on 0, 1. I have to approximate this as closely as I can by something in En complement. Okay, so from homework, given epsilon greater than 0, choose a piecewise linear continuous function g of x with the infinity norm of f minus g less than epsilon over 2. So my original continuous function can be approximated as closely as I like by a piecewise linear function. Now I want to get the slopes of the piecewise linear function very high, and so what I will do is I will add an sk. Now, the slopes for G, well, it only has a finite number of ups and downs, so it has a finite number of slopes, and so they're bounded in absolute value by some constant. The slopes for G are bounded in absolute value by some constant. M. So by choosing k large enough, simultaneously the infinity norm is going to 0 and the slopes are going to infinity. So by choosing k large enough, we can ensure that the infinity norm of sk is less than epsilon over 2, and at the same time and the slopes of G plus sk are all greater than n in absolute value. We fixed n already. So since the slopes of G plus sk, which is just another piecewise linear function, their slopes are going to infinity, we can certainly choose k large enough to get it bigger than n. Well, if all the slopes of a piecewise linear function are greater than n, it cannot be in En. So then G plus Sk is not in En, and consequently it's in the complement. And since I chose Sk to have very small infinity norm, the infinity norm of F minus G plus Sk by the triangle inequality, it's less than or equal to the infinity norm of F minus G plus the infinity norm of Sk. The first one is at most epsilon over 2, and I arranged for Sk to have infinity norm also less than epsilon over 2. So this is less than epsilon over 2 plus epsilon over 2 equals epsilon. Okay, so what we've done here is we have proved that any fixed continuous function can be approximated as closely as we like by functions from the complement of En. But that's just saying that En is complement is dense. Therefore, En complement is dense in C of 0, 1. And then the final step have that each En complement is open and dense, and consequently, by Bayes' theorem, the intersection of all of these things is dense. But as I said at the outset, anything that has a right-hand derivative anywhere is already in one of the Ens. So the things that live in this intersection have no derivatives anywhere. So no function in this intersection can have a right-hand derivative at any point. The fact that it's dense means there's lots of functions in that intersection. And so it's sort of counterintuitive. It turns out that the set of functions that are nowhere differentiable forms a dense set of continuous functions. So in some sense, most functions have no derivatives. This came as quite a surprise originally. So therefore, the nowhere differentiable continuous functions are dense in C of 0, 1. The only problem with arguments like this is it doesn't actually produce one for you, but it shows there are lots of them. So this is fairly typical of bare category applications.
set of functions which are differentiable in C01 are not dense.
No,
Okay.
no, they're dense also,
Okay.
as we're going to see.
Okay.
We almost have that. The piecewise linear are dense. They have derivatives at almost all points. So if we wanted in fact, it might be worth just doing this. So, differentiable functions are dense. So all we would have to do is take piecewise linear one and smooth it at each node. So, just to illustrate, you have some, let's look at one node. What would you have to do? Well, you would have to come up here. You want to be very close to it, so you would just want to round it off near the node. So that would be the idea. One could certainly do that. In fact, we're going to see that polynomials are dense, so that's even better, because polynomials can differentiate as much as you like. I don't really want to get into this. I think the picture should be fairly convincing that one can do this. If I had to do it off the top of my head now, which I'm not going to do, what I would do is I would back off a little bit from the point. So I think the following steps would work. So one, back off from the point. Give myself a little gap. Then I would try to fill in with some polynomial. Now there would be 4 conditions that we would want to meet. Namely, that it should have the same values at these 2 points, and also the derivatives should match. So there'll be call these points A and B. So the second step would be to fill in with the easiest thing to do is take a polynomial. what would you need? Well, you need the values to match at A and B, and also the derivatives to match at A and B. So there are 4 constraints. To match the values at A and B, and also the derivatives, the first derivatives. So if you took a polynomial with 4 degrees of freedom, you should be able to satisfy all of those conditions. So what I would do is I would try alpha plus beta x plus gamma x squared plus delta x. It should be possible to pick values of alpha, beta, gamma, and delta that will match them across there. And it also, I think, should be possible to see that the infinity norm is not going to be very large. And so it will be close to the original function, and in that way we will be able to smooth the function there. It might be interesting just to mention that there are smoothing techniques. For functions, if you have a continuous function and you want to close by find another function that's, say, infinitely differentiable, one can do it in the following way with so-called kernel functions. So to approximate a function f of x, we would take a nice function g of x and form, have you met convolutions before?
Yes.
Maybe in differential equations you've met convolutions. Okay, so the convolution would be h of x is the integral minus infinity to infinity f of t g of x minus t dt. So that would be how you form a convolution. Now, what would guarantee that that is close to f? So for g, we take a function that is infinitely differentiable, supported close to 0, and with integral 1. So this is basically what the function would look like come along, it would be 0, and then it would rise up like this. So support would be between those 2 points. And I would make it rise sufficiently so that its integral was 1. And also make it infinitely differentiable. Now this can be done. And when you then look at the convolution, you will find that this is infinitely differentiable and uniformly close to f. So in the theory of differential equations, functions like this get used to do approximations with very smooth functions without lots of derivatives, whereas your original one might not. Anyway, that's all I'm going to say about that. To get into a discussion of this will take us quite a long way away. But be aware that such things exist. If we have an odd period at the end of the semester, I might come back and show you how this is done.
This is different from delta direct, right?
This is not a direct delta function, which is not a function in the accepted form of the word. But the idea is it looks very much like a delta function. So it has almost no support. A delta function has support at a single point.
So the delta function would be that one where you like take the limit where the points go in.
Right. Yes. Determined to lead me further and further from the path here. So the physicists like to use delta functions, and they think of them as a function at a single point which is infinitely tall and with integral 1. Well, in the mathematical world, that doesn't exist. The physicists are quite happy doing calculations of that. But if you change the context a little bit, this could all be put on a very rigorous basis. And so one can form, you extend the class of functions, and then they become known as distributions. And there's a whole theory of distributions, which includes the delta functions and lots of other stuff too. And it's very useful in differential equations and all over the place. But strictly speaking, delta functions are not quite functions. That I'm definitely going to stay away from. Okay, so let us move on. And I want to talk about approximation of functions. And so the general idea here is the following. For a given continuous function, try to approximate it closely by what I'm going to call a nice function. Now, of course, nice depends on the context that you're working in. If you think about what are the nice functions, well, polynomials are very nice. We know how to differentiate them and integrate them, no problem. Exponentials are nice. Sines and cosines are nice. And so there are various classes of functions that we learn about in calculus, and the reason we learn about them there and not other functions is that those are the nice ones to deal with. So just as a little illustration, suppose you wanted to integrate the integral, say, from 0 to a half of sine of x squared dx. Well, we cannot do that because sine of x squared is not a function that we can integrate. However, we could use a Taylor series approximation. So we can start from sine x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on. That converges to sine x. And because of those factorials, the terms in the series die off extremely fast. And so if we truncate the series at some point, at least on a compact interval, which 0 to a half is, we can expect that the truncated series would be extremely close to sine x. So probably it's very good just to truncate it after the x to the 5th term. So sine x will be approximately x minus x cubed over 3 factorial plus x to the 5th over 5 factorial on the interval 0 or half. So if you replace x by x squared, you'll have that sine of x squared will be approximately x squared minus x to the 6th over 3 factorial plus x to the 10th over 5 factorial, again on the interval 0 or half. So if you don't mind a little bit of error, and you really want to know the integral of sine of x squared, what you can do is you would just replace the sine of x squared by that 3-term polynomial. There you can do the integration, no problem. And consequently, you will get a very good approximation to the true answer. You're never going to get the true answer, but you will be able to approximate it as closely as you like. And this is one way of doing it, just to truncate the Taylor series at some point.
Does this give you like a range of error? Like can you determine the error?
You could get an estimate on the error, yeah. It would be easy to do in this case because the series for sine x is alternating. So the error is the tail, and the tail is no bigger than the first term. So the error in using this approximation would be at most x to the 7th over 7 factorial, and the worst that could be is 1 over 2 to the 7th times 7 factorial, which is a pretty small number. And so that would guarantee you that the error would be extremely small. If the Taylor series were more irregular, a few pluses and a few minuses and so on, then it becomes more difficult to get error estimates. But if you go back to the calculus book, you'll find that there are a couple of formulas for the remainder in the Taylor series. And so often that will give you an estimate. Okay, so this is just a little example to show that it could be worthwhile to approximate even a nice function, and sine of x squared is not a bad function, but for the purposes of integration it is a bad function, but we can approximate it by a polynomial, and then we can do anything we like after that. So that's basically the idea. So the next question is, what classes of functions can you use to approximate any continuous function? evaluate general continuous functions. Now, we're a couple of classes away from actually embarking on that because we need to do some preliminary work first. So, let's start with a definition. Just like this Taylor series example here, we are achieving the function sine x by adding up a series of functions. The functions x, x cubed over 3 factorial, and so on. They add up to sine x. So, on an interval, usually we work on compact intervals, a to b. It doesn't really matter. It could be any interval, or it could be the whole real line. On an interval ab, or an infinite interval, consider a sum of continuous functions the sum from 1 to infinity fn of x. How do we add that up? Well, the same way we add up any series. So first of all, we say that this converges pointwise if for each x the series of numbers fn of x converges. So again, in calculus, you've studied the convergence of infinite series of numbers. We are just now transferring this to functions. And pointwise convergence means you evaluate all of these functions at a certain point. That converts it into a series of numbers, and then you say that converges if the series of numbers converges. So if that happens at each point. However, for most purposes, we would like a stronger form of convergence called uniform convergence. So we haven't quite got to the end of the definition yet. And then we say that the sum converges uniformly if the sequence of partial sums where I just add up the first n. Of course, there's no problem about summing up a finite number of continuous functions. So I can get partial sums So if the sequence of partial sums is a Cauchy sequence, in the infinity norm.
It seems like you might not always have a finite infinity norm if you're working on an infinite interval.
Right, but assuming that you do, if these are bounded functions, of course on a compact set you do. I agree with you on an infinite set, but implicit there that if it's a Cauchy sequence in the infinity norm, that means they'll all have to be bounded anyway.
Okay.
Okay? So let's have a look at an example. On the interval from 0 to b, where b is any number less than 1, the series sigma x to the n equals 1 to infinity, converges uniformly. So why is that? Well, let's have a look at the partial sums. So the nth partial sum is just the sum k equals 1 to n, x to the k. And we want to show that it's uniformly Cauchy. So we have to look at the difference between any two and show that far enough down the line they're going to be very close together. And so without loss of generality, let's take m to be less than n, and then the absolute value Sn of x minus Sm of x is equal to the sum from m plus 1 up to n, x to the k. And this is a sufficiently simple example that we can actually sum it. So this is x to the m plus 1 plus x to the m plus 2 plus x to the n. And now how large can this be? Well, the number is somewhere in the interval 0 to b, and so this cannot be any greater than b to the m plus 1 plus b to the m plus 2 plus b to the n, and it doesn't hurt if I add more terms to make it an infinite series. So this is when I factor out b to the m plus 1, I'm left with 1 plus b squared plus so on. And since b is less than 1, this is equal to b to the m plus 1 divided by 1 minus b. So there I get an estimate that works simultaneously for all x's in the interval 0 to b. b to the m plus 1 over 1 minus b goes to 0 as m goes to infinity. I can choose capital N so that b to the capital N plus 1 over 1 minus b is less than epsilon. And then for m and n greater than or equal to capital N, from what we've already done, we see that the infinity norm of Sn of x minus Sm of x is going to be bounded by epsilon for m and n greater than or equal to capital N. And that means that in the uniform norm, in the infinity norm, we have a Cauchy sequence. So therefore, we have uniform convergence of the sum. So the partial sums form a uniform Cauchy sequence, and that means that we have uniform convergence.